Dear friends, have a greetings of the day. This is Professor Dr. G.S. Wajire from Department of Electronics, Sri Shivaji College of Arts, Commerce and Science, Akola. Friends, today's topic for lecture is Fullwave Bridge Rectifier. First of all, try to concentrate on its title. It is Fullwave Bridge Rectifier. Basically, this is a full wave rectifier, but the diodes are arranged in bridge manner. That's why it is named as full wave bridge rectifier. Already we have discussed this full wave rectifier in detail in last lecture. In case of full wave bridge rectifier, the need of center tap transformer is eliminated, and this is the most frequently used circuit for electronic DC power supply. This bridge rectifier requires 4 diodes connected in bridge manner as shown in following figure A. In figure B, the AC input supply is shown. These are current and voltage waveforms during each half cycle, and lastly this is net output DC voltage available across load RL. Now try to concentrate on figure A. During the positive half cycle of input voltage, that means during this voltage, the terminal M is positive and terminal N is negative. Due to such polarity, diode D1 and diode D3, they becomes forward bias and will conduct the current. During this positive half cycle, the current flows along the directions from terminal M to E. Then it flows through diode D1, then it continues its direction through load resistance, and then it continues to point C, then diode D3 and comes to point N, and in this way it continues its direction and keep the same direction as in this particular case. This is the actual direction of flow of current, and it continues it's like this. And as a result, it produces the voltage across this load resistance RL. During the same period, diodes D2 and D4 are reverse bias, and hence they won't conduct at all. During this positive half cycle, diode D1 and D3 conducts, and as a result we get output voltage across the load. During the next negative half cycle, that means during this particular period, the secondary terminal N becomes positive with respect to terminal M as negative. Due to such type of polarity, diode D2 and diode D4 comes in forward bias and they will conduct. The current direction in this particular case, it will flow from terminal N to F, then to terminal A through diode D2, then through load, then it comes to point C, then it flows through diode D4 and it will continue its direction through this transformer and keeps continue flowing like this. The actual direction of current from point N we can draw like this. It continues through this and it is through RL, then it flows like this, then it flows like this. So direction we can show like this. As a result, we can get output voltage across this load resistance RL. Here I would like to mention that even this negative half cycle, the direction of flow of current through load resistance is same as in last case. That means it is from point A to point B. During this negative half cycle, diode D2 and D4 will conduct and we get output voltage across the load RL. Apart from circuit operation, the equations for this bridge rectifier are exactly the same as in case of full wave rectifier. The average DC voltage VDC equals to twice Vm upon pi. The average DC current IDC equals to twice Im by pi, and the RMS value of current, that is IRMS, equals to Im by root 2. In order to find efficiency of this bridge rectifier, again it is also same as in case of full wave rectifier. So efficiency eta, as usual, it is written as ratio of PDC upon PAC. The value of PDC, it is written in terms of current as IDC square into RL upon PAC means IRMS square into RL plus RD. Here, by substituting value of IDC from equation 2 and value of IRMS from equation 3 above and simplifying these equations, we can get the final equation as in case of full wave rectifier, and that same equation it is written as efficiency eta equals to 81.2%. Thus, here we can say that the efficiency of bridge rectifier is same as that of full wave rectifier. The total wastage of power in this case is also 18.8% only, and therefore due to such higher efficiency and lower wastage of power, the bridge rectifiers are mostly used in high voltage applications. Here I would like to recall that bridge rectifiers are mostly used in higher voltage applications because at a time two diodes are in working condition, and that's why some voltage get drop across that two diodes. Now come to advantages of bridge rectifier. Firstly, we can say that in this rectifier there is no need of center tap transformer. Secondly, much smaller transformer is required. Much smaller transformer in the sense the voltage, current and power ratings of transformer is small. As already we have mentioned that this rectifier is suitable for high voltage applications. Next, it has less PIV rating of diodes. PIV in the sense peak inverse voltage. Here it needs less PIV rating of the diodes. And finally, we can say that the circuit becomes low cost and highly reliable. If we talk about disadvantages of this bridge rectifier, then we can say bridge rectifier requires 4 diodes because the last full wave rectifier it requires 2 diodes only. And lastly, we can say that bridge rectifier is not suitable for small or very small output voltage applications. Friends, in concluding session of this topic, we can say that in case of low voltage applications, full wave rectifier is used, whereas in case of high voltage applications, bridge rectifier is used. So I think let's stop here. Thank you very much.